Let's now apply the Taylor polynomial function for the quadratic or second degree. So degree 2 or quadratic means the same thing for our function cos of x. When we're doing Taylor approximations, you'll note that we need several things. We need f at the point we're doing. We need f prime at that point. And if we're doing the quadratic approximation, we need the second derivative. So it's often nice just to lay things out in a table form here as f, f prime, f double prime in general. And that's pretty straightforward to compute here. We differentiate once, cos becomes negative sine. We differentiate again, sine becomes cos, but there is a negative out front. And then we sub in x equals 0 because we had x equals 0 as the point where we're determining or building our quadratic approximation. And then we're going to fill in these three values. So f of 0 is cos of 0, that's 1. F prime of 0 is sine of 0, that's 0. F double prime of 0 is negative cos of 0, that will be negative 1. And if we think that's the value of the function, here's our cosine graph. It makes perfect sense. The value of the function is 1, the slope is 0, and the concavity, or second derivative, would be negative 1. It's somehow concave down, and this gives us the actual concavity measure. Once we have these three values, it's simply a matter of applying the formula. So our second degree Taylor polynomial, so p for polynomial, 2 for second degree, which is approximately cos of x. So cos of x is approximated by this. This quadratic is going to be exactly f of a, so that's just 1, plus f prime, that's 0, x minus a, our a is 0, plus f double prime minus 1 over 2, x minus 0 squared. Put these in context. Plus, last but not least, f double prime of a over 2 x minus a squared. Again, look for the patterns that'll help you memorize this formula, because it will have to be memorized, but they're very simple. One derivative, 1 power of x. Two derivatives, 2 powers of x. And the dividing by 2 on the second power. Now, it behooves us a little bit to simplify. There's so many zeros here. We have 1, this term is entirely 0, and then we have minus 1/2 x squared. And if you think of what that parabola is, it's opening downwards, shifted up by 1. That would be our parabola here, p2 of x. In fact, we've already done this in sketch form. Can't hurt to do it again. So just to reinforce the message, we can be a bit more detailed here. Here's 1. Here's 1, so pi over 2 is a little bit further. Here's our function. The tangent line is the straight linear approximation, p1 of x, or tangent line. And then our quadratic would look something like this. That would be our p2 of x. While the blue line here is our cos of x. And again, we see that pattern that we'd like to see, which is that the quadratic approximation somehow shares more of the graph, the original graph, cos of x's shape, compared to what the straight tangent line does. The tangent line is still useful because it's simpler than a quadratic, but the quadratic has a little more information in it. All right, why is that over 2 part there? Why do we have this f double prime of a over 2 times x minus a? Why is that 2 there? Well, let's compare the derivative of cos and the derivative of our function. Let's go back to here. Let's compare the second derivatives in particular. We know they had the same first derivative, but let's compare their second derivatives. If we have cos of x as our function, that means that f double prime was equal to negative cos of x, and at x equals 0, f double prime of 0 would be negative 1. Let's compare that to our polynomial. So our p2 of x was 1 minus 1/2 x squared. If we differentiate this twice, let's take the first derivative, we'll get 0 minus, the halves cancel, I'm going to bring a 2 down, minus 1/2 times 2x, and p double prime of x is going to equal, well, these will have canceled already to become 1, and so this will simply become 1, negative 1, and so these two will match. These two will match perfectly. So our approximation and the original function have the same second derivative, but only because of this half here. If we didn't have this half, our second derivative would have been negative 2 of our approximation, whereas the second derivative of our original would have been negative 1. So having this having this 1/2 in the f double prime of a over 2, what that does is guarantees that f of x and p2 of x, the approximation, have the same second derivative at a, at the point we're interested in. If we didn't have that 2, when we differentiated our approximation, we'd get an extra 2 we don't want. So having that 1/2 in the denominator when we look at the multiplier here matches these two functions better than we might have guessed if we hadn't done the calculation. So it becomes very important to have that over 2 part. A final question might be, could we do better? Could we not stop at quadratic? Remember, this is our linear approximation. This is our quadratic. And we might think, well, goodness, why can't we use a cubic? Why can't we use a 4th degree? It will get more complicated as we do this, but it'll get a still better approximation. So if we're willing to trade off in one of these classic balances, we can want more accuracy, we can do more work. If we don't mind a fairly simple function with low accuracy, we can go linear. If we can work with a more complicated function and spend more time building it, we will get a better approximation, in generally speaking, if we build Taylor polynomials that way. So it's worth noting that this is just a first natural extension to quadratic that can be taken further to cubics, 4th orders, in fact, infinite degrees if we want to go that way. Just for the sake of examples here, why don't we take a look at what the cubic might look like, p3 of x. Well, it would be f of a plus f prime of a times x minus a, and we would have the second derivative term like we had in the quadratic over 2 squared. So here's our linear. We built out one more term to get quadratic. And then we can add on the end, well, what would we expect? 3 derivatives, x minus a all cubed. And the denominator, well, think what kind of factors we're going to get out when we differentiate. Here, when we differentiate the quadratic, we got a 2 and it canceled. Here, we're going to differentiate the cubic and get a 3. But we're going to differentiate again later on and get a 2. If we wanted to differentiate this 3 times so that we got the third derivative back, we would differentiate the 3 and get a 3. Then we'd have an x minus a squared. We differentiate again, we'd get a 2. And for some people who have seen this, this can be called 3 factorial, or the exclamation mark, the very loud 3, as we like to call it. So we can see a pattern emerging where if I went to the 4th derivative, it would be 4 times 3 times 2. Second derivative is just 2, or 2 times 1 if you like. And down here it's just times 1. But there's a way to build out a higher degree approximation in a fairly straightforward way based on our extension to the linear and quadratic formulas.